Hi, everybody. Welcome back to Dave's Math Channel. I'm your host, David Tear. This is my continuing feature on the Math Lovers book. And for the last, the last four lectures, I've been talking about Conway's Game of Life, which is my favorite cellular automaton, probably also the most famous one. Um, and today I'm going to talk about a certain type of pattern called Methuselahs. These are patterns that with a very long lifetime, as the name implies, because Methuselah, I guess he was the person from the Bible who lived the longest, at least according to the Bible. He lived 969 years, and he died in the flood, along with everybody else on earth except for Noah and his family, thanks to God, who committed genocide in the entire world except for one family. Good figure. Anyway, let's begin. I'm going to start by again going over the rules of Conway's Game of Life because I think it's a good idea to do that. So there's four simple rules. The first rule says that if you have a dead cell, that's just a cell that's shown in white, that has exactly three live neighbors, it gives birth. So it'll become black if it has three black neighbors. The second rule says that a live cell with fewer than two neighbors dies of loneliness. The third rule says a live cell with four or more live neighbors dies of overcrowding. And the fourth cell says that a live cell with exactly um, two or three live neighbors stays alive. So those are the only rules of the game. And it's played on a square grid. And just to give you an idea of what it looks like, here's an animation. And this is kind of a typical pattern you'll see in the game of life. You can see that, at least it's the start, about half the region is very active. That's kind of the chaotic part of the pattern, but eventually it settles down into stable debris. Um, so that's kind of typically what it looks like. It has a pretty amazingly complex behavior for such a simple set of rules, and this is pretty typical of chaotic systems, by the way. So I said I was going to talk about Methuselahs. So, like I said, a Methuselah is a pattern that lives for at least 100 generations. There's a lot of them. I think when the game was first invented, computer that were capable of animating it were brand new at that time, and they were very slow. And so for a while, I think, people were interested in how big you can make a pattern, starting with a small pattern. That's kind of the idea of Methuselah. So I think one of the first Methuselahs was discovered was this thing called the R-pentomino. The thing showed on the top of this slide. And if you just let this thing run, it runs for a really, really long time. It runs for 1103 generations until it settles down into the stable debris shown below. That doesn't include the gliders that escape from the pattern. And, I thought you guys might be interested in seeing this in action. So I was able to get this on the web, which is kind of unusual. Here's an animation of the R-pentomino in action. I think this is something like 100 generations per second. So after about 11 seconds, settles down. Pretty amazing, I think. And that's just one example, Methuselah. There's several others. These are three other pretty famous ones. The one on the left is because these all have seven. These all start with a population of seven live cells. And they all last for a really long time, especially the Acorn, the one on the left. I believe this has the longest lifetime of any pattern with a starting population of just seven. And then another couple that are really interesting are the B-heptomino. That doesn't live as long. What's interesting about the B-heptomino, you can actually stabilize as used as an engine for what's called a puffer train. I'm going to get into those in a later vision. You can actually make patterns that grow forever using the B-heptomino as an engine. And then the Pi-heptomino is another really interesting one. Notice that this one has bilateral symmetry. So remember what I said about patterns with symmetry in Conway's Game of Blood? symmetry is preserved with time. So the Pi-heptomino will remain. It remains having bilateral symmetry throughout its lifetime. It's pretty fun to watch. Unfortunately, I couldn't find any animation of this on the web, but I thought I'd just conclude by giving you some stats on these four Methuselahs I just described. The R-pentomino has a starting size of five pixels that are on or alive. And its ending size, it grows quite a bit. It grows to a population of 116 after a lifetime of 1,103 generations. So it has a very long lifetime. But nowadays, with computer technology, you can speed it up quite a bit so you can watch it. Watch its whole lifetime in about 11 seconds, like I just showed. And there's other programs that can even run faster than this. And then the Acorn, that was the one on the left I showed in the previous slide. This one, like I said, it has the longest lifetime of any Methuselah of its size or any pattern of its size. It has an ending size of 633. So it grows quite a bit. This one's pretty amazing. And I have seen it in action. And then the B-heptomino, these are the other two I mentioned. B-heptomino doesn't have a very long life cycle. I guess technically I made a mistake here. Though the B-heptomino has a lifespan of 148 generations. So these are all Methuselahs. I just messed up the last column. And its ending size is pretty small, only 28. The Pi-heptomino actually has a lifespan of 173 generations, which is pretty long for a symmetric Methuselah, and its ending size is 55. So those are the stats on these Methuselahs, which I think are really interesting patterns in Conway's game of life. So that concludes my video for today on Methuselahs and Conway's game of life. Thank you for watching. Long live math, and I'll see you guys next time. Bye.